Swayam Prabha. Digital India. Educated India.
So this is what the session is going to be. It's Hello World, right? How many of you have written a Hello World program in C? Everyone. Wow, that's awesome, right? So what we're going to do is we're going to write Hello World again, but then we're going to take a slightly different look at it, right? We look at Hello World in a programming language, and then we move on to writing more complex programs, right? Sorting, linked lists, etc., etc. We're not going to do that. We're going to look at Hello World and try to see what we get that runs on a computer, right? So the theme is quite literally to bring back the C and CS. We look at computer science, we look at different subjects like computer architecture, operating systems, and so on, and we deal with them in silos, right? You did computer architecture in first year, did you? Right, second year, right? I did not do computer engineering, as you have realized. What about operating systems? Third year, okay. And programming languages? Second year, okay. What about system software? In general, linkers, loaders? Third year, awesome. Do you know all these three, four things are related? How? Anyone wants to give an idea of how they are related? That's fine. We'll look at it now. Okay. So we're going to look at how all of these things fit in, okay, in practice, in real life, and we're going to get a concrete view using your computers. So how many people over here don't have Linux on their laptops? Everyone has Linux on their laptops, right? If you don't, team up with whoever has Linux, because we're going to use Linux almost exclusively to do all of the examples, right? And most importantly, ask me anything. Okay, I work in the industry, I work in compiler technologies, so I can give you as detailed a description as possible of the kind of work that we do and of the kind of work that my peers do in these technologies, right? So Abhijat sir already mentioned all of this, so I'm not going to repeat that. And next slide. That's it. There are no slides. Okay. So let's get back onto our computers. And what I'm going to do now is get rid of the slides because we don't need it. And here, what is this thing called? It's a terminal. Awesome. Right? So the first thing I want you to do is type out this program. And you will discover that I don't know how to type. So this is the program that you need to write. Okay, type it out on your laptops. You can see it, right? What does the program do? Prints hello world. What are you saying? What does it print? Hello world. That's what I'm saying. Hello world. No? Okay. So just print this out. You can print any other. You can print a more optimistic hello world if you want, right? That's what we are used to. And once you're done, I want you to do this. GCC. How do you compile the program? File name .c. That's it. And what is the output name? File name. A.out. So all of the programs that you see in the industry, are they all called A.out? No, right? They have a file name. They have an output program name. So always get into a habit of providing an output program name. Always. Okay? As in, even if you are writing a test program, this is how you should do it. Okay, forget that. So A.out is outdated, as in it was a binary format that was invented probably in the 60s or something like that, and that binary format is not even used today. And if you're wondering what a binary format is, we'll probably talk about that later. If anyone's interested in knowing, note that down as a question and ask me later. Done? Oh, you're very fast. That's very good. So did you compile the program? Right? And what happens when you run it? Does it do this? Okay. Anyone who's struggling with it, anyone who's not able to compile this, everyone's able to compile this, right? Okay, great. And you get the right output. Okay. Now, when we did this, when we compiled this program, do you know how many steps of operations happened underneath? Take a wild guess. System software 101. Pre-processing. After that, compilation, assembly, linking. Wow, okay. This is a very, very smart crowd. You'll know like all of the 4 steps, right? So now what we're going to do is go through all of those 4 steps one by one, okay? Did you know that you can actually do that in GCC? Yes? Awesome. So what is the flag to do that? Minus S? What does this do? Assembly. Okay. But then was that the first step? Somebody said pre-processing, right? Yeah. So the first step is pre-processing. How do you get pre-processing? So that's minus E, capital E. Okay. So try this now. Okay. And name the file name hello.i. Okay. I is a standard extension for pre-processed files. Okay. So what do you expect as the output of the pre-processing? Expanded source code. So when you look at this source code, how much more can this be expanded? Is there, this is a very small program, right? How many lines is this? 1, 2, 3, 4, 5, 6, 7, 7 lines. 800 and? That's hello.i, right? What the hell is all of that? Hash include. So what does hash include do? Again, as a chorus. No, one of you. What does hash include do? Includes the header file. What does inclusion actually mean? Redefine. No. Okay, what is that predefined code? Now, okay, there are a lot of abstract concepts. This session that we are doing is going to be very, very, very concrete. So unless you are concrete about what you mean to say, I'm going to keep asking that question. You're right that it includes some predefined code. What is that predefined code? Where is it? How is it included? Printf. What about printf? The definition of printf. Okay. Somebody said declaration of printf. Is it declaration or definition? Are they the same thing? No. Okay. So it's a declaration of printf that you want, right? But then does stdio.h have that? It has all the declarations in the world. Declaration of printf. Right, right, right. Now, how does stdio.h get included? We are back to the same question. What do you mean when you say included? Only the? So the answer is answer is going to be so stupid that you'll probably laugh. What is that? It'll copy the contents of stdio.h and just paste it on top, right? That's exactly what it does. It just opens stdio.h. Where does it open it from? Main folder. What is the main folder? Which library? And what do you mean by library? We are going to get answers to all of these questions. If you don't, somebody please note them down. If you don't get answers to any of these questions, ask me later. What is a library? Okay, that's one outstanding question that we'll keep aside for a while. Right? So where is stdio.h? The question has not been answered yet. The GCC include folder. What is the GCC include folder? Is there something called as a GCC include folder? There is, but stdio.h is not in that. User include, awesome, right? So you have a directory called user include. This is the default include directory. This has a lot of header files, right? And these header files are not necessarily, in fact, most of them are probably not from GCC. Okay, they are from a library. Most of them are from a library called glibc. Okay, is a standard C library. We'll keep hearing this name again and again, and I'll probably delve deeper into that project as we go ahead. Right. So now we know where stdio.h is. Right. Is it in that directory? Let us confirm. Yes, it's there. Right. And if I open it, I can actually read it. Right. There's a bunch of things in there. So now we know exactly. Now we can very concretely define what pre-processing does. Right. We see stdio.h, the include, and we pick up that file, expand that in there. Now we look at that entire file again. Are there any other includes? Are there any other includes in stdio.h right now? There are, right? There's bits types file, and libio, and so on and so forth, right? So recursively, it will open that file, right? That is one aspect of pre-processing. The other aspect of pre-processing is macros, which is like a minor language by itself. If not defined, then define a macro, you know. And then there are other macros which allow you to paste strings together and all. So it's a very small constrained language which does a limited set of things, but it allows you to, it gives you a very powerful mechanism to conditionally compile code, right? For example, if you are doing stdio.h include, let us say you include another header which also includes stdio.h. What happens then? You include stdio.h twice. Is that a good thing or not? No. So there is a very simple mechanism which says if not defined macro, define that macro. Okay, and everything else happens if that macro is not defined. What that does is that if you include stdio.h the second time, your contents won't get replicated. You get all of those declarations exactly once. Okay? So this is the essence of pre-processing. Now let's take a look at the pre-processed file. As you can see, it's 844 lines long, right? Where is your code? It's buried right at the end. Those your 6-7 lines are buried right at the end, right? And what did we need all of this for? We needed it for, why did we need stdio.h? For printf, right? For the printf declaration, so that we can tell the compiler that I am calling this function printf, and the function has the following parameters, and this is what it returns, right? Let's look for the printf declaration then. I want you all to do that. Look for the printf declaration in there. So, I found D printf, VD printf, VSN printf, SN printf, there, this is printf. Did you find it? Okay, anyone who is having trouble finding printf? For minus capital E. Capital E. That is the switch. Everything else remains the same. Yes. Everyone found this? Okay. So, now you know that just for this one printf, we included 840 lines, right. So, can we drop everything else, just keep this extern int and build the program successfully, or will it fail for something else? Is there some other mysterious feature that stdio.h adds that we are not aware of? Or is it capable of doing that in the first place? How do we find that out? How do we find out whether this is sufficient or not? We delete everything, we keep this in place and we compile it. It works, right? So, let us try that. If any of you is lagging behind, wants me to stop to catch up, just let me know, okay? So, I am going to open this, I am going to turn syntax off so that I can actually see something. Oops. There you go. So, I keep printf and this. Okay. So, this is going to be my new C source code. I can keep it as .I, it does not matter. Okay. We will take a closer look at the function later, the declaration. Now, if I say gcc minus o hello, hello.I, works? Okay. This works perfectly, right. So, there is nothing else that a header file adds other than declarations. Okay. So, as such, if you are looking at any program, if you are able to remove all of the cruft. So, the other 800 lines that you saw, 840 something lines, they were all cruft in the context of this program, right. So, you could have technically just written this program and that would have been sufficient, correct. Why do not we do this? Why do not we do more of this? Any guesses? Your guess could be wrong, that is fine. Why don't we just always write extern int printf and whatever, and why do we include 800 lines of cruft?
Every time writing is not feasible and remembering also.
Why is it not feasible? I am writing a hello world program, this should be fine, right? Okay. So, you are kind of on point. What happens is that you are not going to write hello world all the time. You are going to write something that is a lot more complicated, and there are a few thousand library functions in the C library, and if you are going to write externs for all of those, that will take up a lot of your time, and in most cases you will be wrong, right, you will make mistakes in that. So, that is the reason why you do not do this, but then this is important to know, right, because now you know that the only reason you have the header file in a hello world program, the stdio.h, is for the printf declaration. There is nothing else that you need over here, absolutely nothing else. Let us modify the program a little bit. Okay. If I say size t foo, because I don't know a better variable name. I'll just there. Size t foo equals 42. Okay. And what is the format specifier for size t? Percentage ZU. Okay. And I print foo. I'm not going to compile this, but tell me, will this work? So, to understand whether this will work or not, you need to become the compiler and see what the compiler sees over here. The compiler sees this in this program, it sees main as a symbol. It's a function definition, correct? A function definition it can handle, because it's just going to build a tree for it and generate assembly for that. That is perfect. Now, you have foo, which is a type, which is of type size t. Then you have printf as a function, right? And at this point, it's going to start wondering what is printf. And then you give it the declaration, correct? And then it says, okay, there is a declaration that tells me what printf is. That tells me that the arguments that printf can have and the return type that it has, that it returns, right? So, printf is also sorted. Return is a keyword, so I understand return, right? And return a constant number, correct? So, now I have compiled everything except size t. Now, it all depends on whether the compiler identifies size t as a type or not, okay? And the compiler does not. The compiler does not identify size t. Size t is provided by a different header, which is essentially a type def. Okay. Now, have you ever seen size t as a type before? How many of you have not seen size t as a type? Most of you, right? So, I will just tell you what size t is. Size t is the size of a pointer, essentially. Okay. There is a ptr-t, which is precisely the size of a pointer, but then size t is unsigned long for that machine. Now, if you are on a 32-bit machine, it is different. If you are on a 64-bit machine, it is different, correct? That is the reason why you have a standard type called size t, which will differ from machine to machine. And it is glibc which will look at the machine and it will provide you macros which will say for a 32-bit, for a word size 32-bit, size t is 32-bit, for a word size of 64-bit, size t is 64-bit. Okay. So, you need to provide a type def for size t. Okay. So, you quickly realize why you need those standard includes. It is because you do not want to do work that is unnecessary, right, when you are writing large programs. But then if you are writing embedded programs, if you are writing compilers, if you are writing low level runtimes, you might have to end up doing all of these things, right, especially when you are doing very early initialization. Do you understand what I mean when I say very early initialization? I am guessing not, but you will in a while, right. So, now we have pre-processed a program and we have our pre-processed code. Next thing we will do is generate. What do you get after that? Assembly, right? Okay. So, let's exit this. I will generate hello.i again. This is how I generated hello.i. Now, from hello.i, how do I generate hello.s? You already told me this, right? It is minus capital S, correct? So, now let us look at our assembly. Now, this is fairly straightforward. I think all of you must have actually seen this in some form or the other at some point, right? How many of you over here are comfortable reading assembly? 1, 2, okay, fine. So, do you know what this is doing? What is CFI start proc? Oops. Okay, let us go from the first line. So, First line, what does it say? The file is hello.c. So these are called assembly directives. Okay. So and then it tells you it's in the .text section, and then there's read only data, and then you have a function, right? Now let's go through the function. What does it do? It pushes the which register is this? Base pointer, right? So this is which architecture is this assembly for? 64-bit what? What is the CPU? It's an Intel 64-bit processor, right? Now this is very important because there are, so you need to appreciate the fact that there are probably a dozen or more different CPU architectures out there. Okay, Intel is just one of them, right? If you're going to work in the server world, you'll probably mostly only deal with Intel servers and desktops, right? That is slowly changing. You are getting desktops with ARM architecture CPUs as well now. Your Chromebooks are all ARM architecture CPUs. Your phones are all ARM architecture CPUs, right? They can be 32-bit or 64-bit. So first thing that you should think of when you're looking at assembly file is, what is the architecture? You know why? There's another reason for it, because assembly programming is hard. Assembly programming is very, very difficult. That is coming from a person who has done 7 years in assembly programming, right? It is very difficult, and you are not expected to know instructions by heart. You need to pick up a manual. So the first step when you look at this is, okay, this is Intel x86-64. Let me pick up the Intel x86-64 manual, okay, and then start trying to figure out what it means. Okay. But then there are some primitives that are always there on most processors. So you know that push means push onto stack. Okay. What is a stack? Stack is memory. It's on the RAM. It's a location on the RAM, right? So we'll see precisely what the stack is later on. Okay. So it pushes on the stack. Then you have move from stack pointer to base pointer. So you preserve your stack pointer. Then you move a certain return address, I am assuming. Yes, it should be a return address to, no, where is that? To this register called EDI, and then I call this function called puts. What is puts? Have you heard of the puts function ever? Input, output. So I know it could be input or output, nothing else. So is it input or output? Output. Okay. What does it output? A string, right? But then where does this come from? We wrote printf, right? So where did this come from? Where did puts come from? Okay, hold on to that question. The next thing we do is pop the base pointer, which means the base pointer goes onto stack and then we return. Okay. Now one very interesting thing over here is all of these instructions. In many ways we did not do this. Did we? No. This was something standard that the compiler added. Okay. And this is called a function prologue. Okay. And at the end of the function, I pop RBP. Okay. The CFI directives we will probably not talk about it. If you are interested in knowing, we will talk about it later. We pop RBP and then we return from the function, correct? So these two things, they are called the function prologue and the epilogue. They are standard for every function that you define. Okay, every function that you define, it would be a standard. and it would be a standard for every architecture. So, this is the prologue epilogue format for x86-64, okay, where it is necessary to save the stack position into some register, and at exit you pop that stack pointer, right. On ARM it will be slightly different, and this standard interface, it is called an ABI, that is called an application binary interface. It is published by the hardware manufacturer. So, Intel will publish an ABI saying that this is how you call a function, okay. And now you look at puts. You pushed a pointer into EDI, okay. EDI is essentially RDI, the 64-bit equivalent is RDI, and then you call the function. This is also part of the ABI, okay. It is basically telling you how do you call a function. So, the way you call a function on x86-64 is you put your arguments, function arguments in registers RDI, RSI, R10, R9, R8. Okay, don't tell me why it is R10, R9. Don't ask me why it is R10, R9, and R8, and not R8, R9, R10, or whatever. Not a sequence. That is an architecture decision, right? That they won't tell us exactly why. We can make guesses, but that we can talk about later, right? But then that is a standard format. Why would you need such a standard format? So, when you are writing software, right, you might be writing like a plugin, correct? Do you know what a plugin is? A plugin is a library which provides a set of functions, right. Now, when you have to call those functions are not written in C. They were written in C maybe at some point, but they were compiled into a binary machine code, essentially assembly, right, if you are looking at the human readable aspect of it. Now, when you are calling a function in assembly in machine code, you need to know which registers your arguments go into. You need to know how to actually invoke that function, right. Call is one way to do it, but how do you provide the arguments? So, there is a predefined way to do that. So, on x86-64 it is RDI, RSI, R10, R8, R9. On 32-bit it is pushing arguments onto stack. On 32-bit there is also a fast call method, which is I think EAX, EBX, ECX or something like that, right, where you put arguments into those registers instead of pushing onto stack. Why is it a fast call method? Why is it faster putting on register than pushing on stack? You're putting into memory instead of direct register access, right. You're actually going from that chip die, from the CPU chip die, you're walking all the way to the DRAM, pushing words on there, and then you're coming back and resuming execution, right. So, typically if you look at it in CPU latency terms, putting into register would be what, 1 cycle, and going to RAM and back is 400, 500 cycles, right. So, these are things that you need to consider when you are designing an ABI, right. So, now any questions on ABI so far? Mnemonics, in what sense? The instruction mnemonics. So, the instruction mnemonics are part of the instruction set. Okay. So, your instruction set defines what instruction you can execute, right, and then you will have a register file which tells you the register names and so on and so forth. So, with that you can design whatever the hell you want. ABI is just a conceptual limitation where you say if you want to call a function, you have to set it in this way. Now, if you are writing a programming in assembly and if you are going to never call any function on the outside, then you can design a faster ABI for yourself within, where you can say that all my function calls, let's say for some reason pushing onto stack is faster for you, okay, for whatever reason. So, I am going to push only onto stack, I am not going to use up registers. Let us say there is very high register pressure, like in 386 machines, right, the 32-bit machines. So, you can make that decision by yourself within yourself, right. The fast call method is essentially that. The fast call ABI for 32-bit is essentially a contract within glibc, where we say within glibc we are going to use fast call for function calls because we want to optimize. We do not do that for any function calls that are outside of glibc. Okay. So, it is basically it is an artificial contract. It is not a machine limitation. It is just something that you put in there so that you can talk to programs and libraries that are written by anyone else in the world. So, it is a standard that you arrive at. Okay. Any other question? Okay, great. So, now we come back to the question of what is puts and where did puts come from. We wrote printf, right. Let us take a look at our program again, just to be sure that I did not trick you. It is printf, right, correct. Now, one way is that there could be an alias. So, the C program in stdio.h, there could be a hash define saying hash define printf puts. Is that possible? No? Why is that not possible? I can't hear you. It's predefined, but I could predefine it as a macro, which is essentially puts. It may be ambiguous. Okay, so let me just first look at the man page for puts, okay, so that we know what we are talking about. So, this is our man page for puts. What is puts? Puts is just a file point, a string and a file pointer, okay, which is your stream std out, right. And so, sorry, that is f puts. So, you have puts where the stream is implicit, which is your standard output. Okay. So, you are essentially providing only the string, which is what is happening, right. You have RDI, EDI, which has the string pointer, that is it. We are not actually looking at anything else. So, how is this different from printf? So, printf, oops, right. So, printf also takes a string, but it is a format and then there is a variable number of arguments. Okay. Now, what happens if there are no arguments to printf other than just the format? Similar to, it is identical to puts, right, it is identical to puts. Okay. Now, with printf, okay, now I would like you to take a leap of faith and imagine how puts might be implemented versus how printf might be implemented, okay, in the context of printing the string. How would puts be implemented? Consider the string as a character array and it will go print character, print, found a null character, return, right. That is how puts works. How would printf work? Right, correct, then it will start printing, right. So, there is this whole lot of processing that happens first and then there is a printing phase, right, with printf, whereas puts is just blindly print, correct. So, which is going to be faster if you have to print just the string? Puts, correct. So, and this is a very straightforward unambiguous optimization. Okay. Now, who has done that optimization? In this, who did that optimization? GCC did that, right. Oops, what did I do? There you go. So GCC did that optimization. So GCC optimized a printf with just one argument into puts. Okay. This is one of hundreds if not thousands of optimizations that GCC does. All right. And I think next week in Uday sir's sessions, you'll probably take a deeper look at how these optimizations happen. So a lot of them are mathematical transformations and analysis, right, data flow analysis. But then there are these little gems that actually come from the industry in most cases, because there is where they are looking to squeeze that last 1% out. And this is how people squeeze the last 1% out when it comes to optimizations, right. Then there is, if you have like multiple function calls, which could, like for example, string n copy versus string copy, there could be transformations in there as well, which allow you to choose the faster routine, right. So GCC does that, and GCC only generates assembly. Okay. GCC does not produce object code. All right. There is something called as fdump tree and fdump RTL arguments to GCC, which allows you to analyze the various passes inside GCC when it comes to optimization, but I won't go into that again. That you'll probably learn a little more later. So now you have the assembly file. Is this executable in the machine? No. So what do you need? Binary. So let's zeros and ones. Let's get the zeros and ones out. So what is a program that you would invoke for this? Okay, let's not go into the assembler. Let's allow GCC to invoke the assembler for you, right? So how do you do it? -c, right? Hello.o, okay, because O is the standard extension for object formats on Linux, right. So I am compiling only. So this is only compiling into object code. We are not doing anything else. And if you look at large complex projects, this is a command line you will see very, very often in makefiles. Okay. You will be compiling lots of code into object files, and then you will be combining them into executables and libraries. Okay. So did you see this? Now, how do I see this object code to see what's inside? Can I do less? Is this possible? Let's see. Whoops. What is all this? I don't remember writing at the rates. That's not right, right? So it is a binary format, correct? So how do I analyze the binary format? XXD or hex dump, basic XXD, is it? Okay. This. Now what do you get, what do you understand from this? Right. So let's pipe it to less. Okay. There is still things that you can understand from this because of the strings in there. Like it tells you that the first 4 or 5 bytes tells you that it's an ELF file, right? And what is an ELF file? So ELF is called the extensible and linkable format. Okay. It is a format, it's a binary format for any program. Okay. So it could be a library, it could be a binary, it could be intermediate object code. Right. It is an extensible format to define how a binary would be laid out in memory or on the disk. Okay. Right now, where are we? Are we in memory or disk? We are on disk, right? The object code is on disk. It is not being executed, right? So now we are looking at the ELF format, and looking at the ELF format just like that is utterly useless, right? Because what you have is object code, you have opcodes and all that encoded in binary, and there's nothing you can do with it. So you use a tool called objdump. So in this entire process, I'm going to introduce a lot of tools. Just note those down whenever you're doing them and explore those tools further, because there's a lot you can do with those tools than just looking at dumps like this. Okay. Now, suddenly you see this, which is so much nicer, right? So now this is basically assembly code. It has this is called disassembling, right? It has disassembled binary code to show you assembly. Okay, and this is how you can look at the code of any program on your operating system. Any program. So I can use obj dump. And what is your favorite program? ls? ls? Okay. So ls is in bin. Okay. This is the assembly code for ls. All of this is assembly code for ls. Now the only thing that you need to know is to understand how to traverse all of this, right? And you shouldn't have to do this, because this is really hard. Like I said, assembly code is hard. It's hard to read assembly code. That's why you how do you read ls code otherwise? It's an open source project, right? So it's part of a package, I think, called core utils. You just download the source code for that package and you read the source code. It's in C. Right? That's the power of open source software. You as a student don't have to pay anyone to do that. You can just download it off the internet and look at the source code. But for anything that does not have source code available, this is one way to look at it. Right? And then when you're doing diagnosis of programs, right? So this is your assembly code for ls. Like that, you can look at assembly code for anything in the world, right? By using obj dump. Let's get back to our example. So now your object code looks more or less the same as the assembly code, right? Okay, except that the call is a little weird. It is calling some E, right? Does that even make sense? It calls the next, so E is the address and this is E, the address, which is the next line. Does that make sense at all? It doesn't, right? So this is a placeholder. It is saying call a function. It doesn't yet know what the function is, right? Now, how are you going to tell it what function it is? You use the linker, right? So let's get to the linker. So now you're going to output hello using hello.o. Okay. Now, before you open up hello under obj dump, can you guess what would be in that file? There would be main and the definition for main, right? What else would be there? So what do we do in main? Let's look at the program again.